This video is on the stereochemistry of SN2 reactions. What happens if we try to do an SN2 substitution at a chiral center? Well, there are three possibilities. One, we could get retention of configuration where the chirality remains the same. Two, we could get inversion of configuration where the chirality flips. Or three, we can get racemization where we get a 50-50 mixture of both chiral centers. In SN2, the nucleophile has to attack the electrophile from the opposite direction of the leaving group, what we refer to as a backside attack. This causes an inversion in the reaction. So SN2 causes inversion. You practice. What would be the product of this reaction with specific stereochemistry? You may pause now. And here is the answer. So due to the directional nature of the backside attack, sterics become very important. The nucleophile needs clear access to the electrophilic site. Bulkier groups get in the way, increasing the energy required for a substitution to occur. This decreases the rate of reaction. We can see this clearly here. With methyl chloride, the rate of the reaction is 30, as there are only hydrogens theoretically in the way for this axis. So this is very accessible carbon here. However, ethyl chloride, you already have a methyl group blocking the way. With an isopropyl group, you have two groups blocking the way and you have even less access. And with a tert-butyl group, well, let's just say we cannot access that carbon because all the methyls are in the way. Even if the bulk is further away, it will have a major effect on the reactivity. So in other words, if you have a bulky system, it's unlikely you will get effective SN2 reactions. At least it will be very slow. We can summarize this by stating that SN2 will not occur on tertiary carbons, period. It just can't happen. But then the rate of reaction increases as you go from a secondary carbon to a primary carbon to a methyl electrophilic site. What about resonance, I hear you say, because of course. Well, turns out resonance actually stabilizes the transition state. So having more resonance near an electrophilic site, you are going to have a faster rate of reaction. As can be seen here, the allyl group has a relative rate of 40. That's already a substantial amount of resonance. If we have a phenyl group, the relative rate increases to 120, whilst the carbonyl takes it to 10 to the power of 5. You might be thinking, but wait, Dr. V, aren't those things bulky? And even though initially, if you look at it, you are correct, we got to remember that these are sp2 carbons. We have double bonds. So they are relatively flat. So in that sense, they are less bulky because if they rotate in a certain way, you're going to end up with this empty space where an sp3 carbon would be filling up space. So in other words, anything with double bonds is less bulky than something with single bonds. So which one of these two alkyl chlorides would react faster with sodium hydroxide? You may pause now. And yes, the aromatic, or the one with the double bonds with resonance, is going to react much faster. It's less bulky and it has resonance stabilization on the transition state.